Today we're going to cover 5.4 solve trigonometric equations. So by the end of the lesson you should be able to solve trig functions algebraically. You should be able to solve both linear and quadratic trig equations, and you're going to solve them generally between 0 and 2 pi. And you're going to be able to solve word problems as well. So we got a lot to do here, so let's get going. So this is a trig equation. It's got a trig function in it and it's equal to something. What we're going to do, this is a linear one. We know that there's no squared here. There's no squared on this one, so that's a linear trig function as well. But this one's got a squared in it, that's the highest exponent. So this one is a quadratic trig equation. Okay. So to solve linear trig equations, you want to isolate, just like you would solve a linear equation. You're going to isolate for x. Well, you're going to do that you're going to isolate for the trig function. If you have reciprocal functions, you're going to change them into their primary trig ratios. And then you're going to use the inverse function on your calculator, or you're going to use special triangles in the cast rule to find your values for your angle. All right, enough talking, let's get at it. All right, solve the following equations between 0 and 2 pi. Give exact answers where possible, otherwise round to 2 decimal places. So if I've got sine of theta equals negative 1 over root 2, I've already isolated sine theta, and now all I want to do is figure out what my angle is. And I know that the angle that generates a ratio of negative 1 over 2 is one of those special angles. And if I draw a little picture, I know, oh, this is too small, that it's pi by 4, right? Pi by 4, 1, 1, root 2. And that the sine of pi by 4 is going to be 1 over root 2. That's the positive. But we know this one's negative. So what I know so far is that if I take the inverse sine of negative 1 over root 2, I know that my reference angle, my angle between 0 and pi by 2, or 0 and 90 degrees if you want to think back to grade 11, is going to be pi by 4. But I know that sine is negative, this ratio is negative, so sine is negative in quadrants 3 and 4. So I need to solve this for quadrants 3 and 4. So if I'm drawing a picture here, there's quadrant 3, my angle, there's quadrant 4. So I know that this is my first angle and this is my second angle. I know this first angle is going to be pi by 4. And I know then that I have to add pi to pi by 4 to get where this angle terminates in quadrant 3. So the first angle, I'll call it theta 1, is going to be pi plus pi by 4. So theta 1 is going to equal 5 pi by 4. And theta 2, second angle, the second instance of this between 0 and 2 pi, the one that also will give me a negative ratio, is going to be over here, and this is going to be pi by 4. So it's going to be 1 pi by 4 short of 2 pi. So I'm just going to say 2 pi minus pi by 4, and theta 2 then is going to equal 7 pi by 4. Okay? Therefore, and I need a therefore statement because we can get a lot of different angles here, possibilities for these questions. So please summarize your answer. So therefore theta 1 equals 5 pi by 4 and theta 2 equals 7 pi by 4. Okay, so the key here was we noticed that this was the ratio for a special angle. I noticed the square root of 2, and the other thing that I had to notice was that it was a negative. Okay, so I knew that this was our reference angle was pi by 4, but I also knew then that I had a negative ratio here, which is why I knew that sine had to be negative in quadrants 3 and 4. Okay, let's try the next one. So 5 sine theta equals negative 2. I'm isolating here. I'm going to divide through by 5 on both sides, and I get negative 2 over 5. Now when I stare at that ratio, I don't see anything familiar. I don't think that this one is part of a special angle, so I'm just going to go ahead and use my calculator, make sure it's in radian mode. So theta calculator is going to equal sine inverse of negative 2 over 5. I'm going to calculate with my calculator in radian mode the inverse sine of negative 2 over 5. And when I do that, theta calculator is negative 0.41. So we'll get it to approximately 2 decimal places. Okay, so we have to think about that answer. Number one, is that an angle between 0 and 2 pi? And of course the answer is no, because it's negative. So our calculator lies. It doesn't out and out lie, but it gives us, it's just a little bit of a fib. So it will give us some information, and this is the information that it's providing to us is the actual reference angle, which is the positive value of this, 0.41. So what your calculator does is it gives you the angle that's the closest to the x-axis. So for this one, there are going to be two negative angles, or angles that provide, sorry, not negative angles, but angles that provide a negative ratio. So there and there, somewhere in quadrants 3 and 4. But the closest one would be if you were going this way. You could get to this one the fastest. So that's what your calculator does. It gives you the negative 0.41. Well, we can take that information then, and we can figure out what the these two angles are based on that, because we know that this is really our reference angle if it's positive. And so we know that sine, again, we'll just write this down, is negative in quadrant 3 and quadrant 4. And you know what, I normally, and I'll just go back to that first example, I normally write which angle I'm finding. So over here I found the quadrant 3 angle. Over here this was the quadrant 4 angle. I like to just keep that organized. Okay, so I'm going to do that again. I'm going to say now that theta 1, the first instance over here in quadrant 2, is going to be equal to pi plus, oh sorry, not pi, because I've got approximate radians here, so I'm, instead of using pi, I'm going to use 3.14. And it's approximate. 3.14 plus 0.41. So theta 1 is approximately equal to 3.55. And theta, and we'll call that rads. Theta, this is the quadrant 3 angle. Theta 2 is our quadrant 4 angle, and we get a quadrant 4 angle by taking 2 pi, which is 6.28, and subtracting our reference angle of 0.41. And when I do that, 6.28 minus 0.41, 5.87. Right. Okay, this is the quadrant 4 angle. Therefore, theta 1 equals approximately 3.55 rads, and theta 2 is approximately equal to 5.87 rad. Okay, that's solving linear trigonometric functions. Okay, so isolate and then check your domain, make sure you're solving for the proper domain, and you're on your way. All right, let's solve some harder ones, some trig ones. So remember, to solve a trig equation is not the same as solving a linear equation. You don't solve a quadratic trig equation the same way. you have to factor in order to solve it. So you're going to set one side equal to 0. You're going to factor it. And if you need to replace your trig function with a variable to help you see how to factor it, then feel free to do that. So you're going to go ahead and factor it. And if you have replaced it with x, you're going to put it back in once you solve for x. And then you're going to solve just as we did our linear factors before. Okay, so I'm going to say this is let sine theta equal x, and so this is going to be x squared minus 1 equals 0. Now, once you've done this a few times, you don't have to do this substitution technique. You may be able to factor directly from trig form, but it is really helpful to do this at first. And if I were to solve this, I could isolate this one. This is one of those rare quadratics where you are allowed to isolate because there's no middle x term here. But be so careful. So I could do this. X squared equals 1. Take the square root of both sides and have x equal to, what students will do is they will forget that the square root of 1 is positive and negative 1, right? And then you're going to replace the sine, or x, with sine theta equals plus or minus 1, and then you're going to solve from there. You can do that. That's not a problem. But just make sure that you remember to take the square root, the positive and negative square root. So I'm not going to do that because I want to avoid any mishaps here. So I am going to go ahead and factor that. It's a difference of squares. So it would be x minus 1, x plus 1 equals 0. I'll solve for x, and so I get x equals 1, x equals negative 1, and I'm going to replace then x with sine theta. So sine theta equals 1 and sine theta equals negative 1. Well, where does sine theta equal to 1? Equal 1, I should say. We know this is our unit circle. This is where our 1s and 0s come in, are those special ratios. Okay, so where is sine equal to 1? Well, sine is here, so sine has to be equal to 1 at pi by 2. So I'm just going to say theta equals sine inverse of 1, and theta is going to equal between 0 and 2 pi. There's only one instance where sine theta equals 1, and that's at pi by 2. And you're going to do the same thing here. Theta equals sine inverse of negative 1. And so theta, where is sine negative 1? Down here at 3 pi by 2. So I'll just do my therefore up here. Therefore, oopsie, I should have done theta 1 and theta 2. Sorry. So theta 1 equals pi by 2. Theta 2 equals 3 pi by 2. Done. Okay. I know it's not so easy. So let's let cos theta be represented by x. And so we would have 6x squared plus x minus 2 equals 0. When I factor this, I'm going to get 3x minus 1 times 2x plus, minus 2 plus 1. Double check that. 6x squared plus 3x. Oh, no, that's not right. This is plus, and this is minus. I'm being lazy tonight, and I didn't want to bother doing our shortcut method. So 6x squared minus 3x plus 4x minus 2. Okay, so if I'm solving for x, I would get x equals negative 2/3. You can just set that whole factor equal to 0 and solve for x, right? So this is going to be x equal 1/2. If I put a half in there, I get 0. If I put negative 2/3 in there, I get 0 as well. Okay, so put our cos theta back in, and we get cos theta equals negative 2/3. And we get cos theta equals 1/2. Okay, so Negative 2 and 3. Well, those numbers aren't part of a special triangle. Certainly the 2 is, but the 3 would have to be a root 3. So I'm just going to have to go ahead and use my calculator here. So I'm going to say theta calculator equals cos inverse of negative 2/3. And let's see what my calculator gives me for that answer. So let's see. 2 divided by 3 and then second cos. I'm getting 2.30. Okay. Now, let's think about where this is an angle, right? Theta is an angle. So where does 2.3 land in our Cartesian plane? Well, if I'm talking about approximate radians, this is 1.57, this is 3.14, this is 4.71, and over to 6.28, or 0. So 2.3 is somewhere between 1.57 and 3.14, so it's in quadrant 2. So it's actually giving us one of our answers because we can see that our ratio is negative. We know cos has to be negative in quadrant 2. So this is actually giving us one of our angles. But we need to generate the other angle, the angle that's also negative in quadrant 3. And so what I would like to do, if I drew the angle here, 2.3, that's going to land us, say here, this is 2.3. What's left here? That's our reference angle. So if I want my reference angle, beta, I'm going to have to take 3.14 and subtract 2.3 from it. And so I think that's 1.64. I'm really tired right now, so I'm going to just cheat and use my calculator. And it's going to be 0.84, sorry. Okay, so my beta is 0.84, and now I can generate my quadrant 2 angle. Well, I already have my quadrant 2 angle. So my first answer is going to be 2.3. That's my quadrant 2 angle. And I know, and I can remind myself, that cosine is negative in quadrants 2 and quadrant 3. And I know I'm looking for negative because it's right there, right? That's my negative ratio that I'm finding the angle for. Okay, so the first angle is approximately 2.3. My second one, I have to generate from my reference angle. So my second angle is over in quadrant 3. So it's going to be up here somewhere. And I know that I have to take pi and add my reference angle to it to get the quadrant 3 angle. So this is going to be 3.14, oopsie, 3.14 plus 0.84. So theta 2 is approximately 3.98 radians, and that's my quadrant 3 angle. So I'm not finished. That was only one of these, so this was only one of my solutions, right? So far I've got that theta 1 and theta 2 came from this one, and now I'm going to see what other thetas I can get that produce a ratio of 1/2. So 1/2, you should know, is a special angle, right? So let's just draw our triangle, and that might help us. So if I draw my pi by 3, pi by 3 triangle, I've got root 3 here, I've got 1 here, and I've got 2 here, and the cos of this would be 1/2. So I know that beta is pi by 3. I'm proving it with this diagram, okay, and I want you to draw me the diagram. I know then that my cosine is positive in the other two quadrants. So I'll just write that out too. Cos positive in Q1 and Q4. All right, so if my reference angle is pi by 3, I know that I have to be in quadrant 1. I know then that my third angle, theta 3, is pi by 3 because I have to have one in the first quadrant, and this is a first quadrant angle. Now my last angle, theta 4, is in quadrant 4, so I'm going to take 2 pi minus my reference angle of pi by 3, and that's going to get me that last one. And so theta 4, so this is my quadrant 1, and my theta 4 is going to be 6 pi by 3 minus pi by 3, so this is going to be 5 pi by 3. And that's my quadrant 4 angle. All right, so I found 4 angles that will satisfy this trig function, and so I'm going to put a conclusion in there. Theta 1 equals to approximately 2.3 rad. Theta 2 is approximately 3.98 rad. Theta 3 is approximately, theta 3, where's theta 3? Is not approximately, it's exactly pi by 3. And theta 4 is exactly 5 pi by 3. Okay. All right, one more example here of a trig one. So this one's a reciprocal one. I'm just going to, oopsie, what happened? So it's sec squared, there's a squared there, x plus 2 sec x equals 0. So let's just start here underneath here. So I am going to, I'll just change the color of my pen too for this one so it doesn't get all mixed up. So sec, was it just plain sec squared? Yep. Sec squared x plus 2 sec x equals 0. Okay, so if you'd like, we can let x be represented by sec x, and so we would have x squared plus 2x equals 0. Then we're going to factor this. Well, there's only one way to factor it is to take out the common factor, and then we can solve. So x equals 0 and x equals negative 2. Let's replace x with sec x. So we end up with sec x equals 0 and sec x equals negative 2. Okay. So sec x equals 0. So if I'm trying to find out what sec inverse of 0, but I know that sec x is related to cosine, and I'm wondering, okay, if I wasn't sure what to do here, I think I would probably draw out my little unit circle because I'm suspicious that if it's equal to 0, right, that it might be one of my unit circle values here. So let's go and have a quick peek at this. Okay, so sec is related to cos. It's the reciprocal of cos. So it would have to be a reciprocal of cos. The original would have to be undefined then, right? Because we would have had division by 0, so that when we flip it, it's 0. Well, none of these is going to work because all of these are defined. And cos is never undefined. Cos is continuous, right? There are no asymptotes for cos. So if we go back now and we think about the graph of sec x, do you remember what it looks like? We'll just quickly sketch something out. I don't remember what it looks like, but I know what cos looks like, right? Cos looks like this. And so there are zeros here and here, which means there are asymptotes on the reciprocal here and here. And so remember, this was, here, I'll use a different color. This was a shared point. And this was a shared point. and up here at 1 was a shared point, and we were approaching the asymptotes. So this is what seq looks like. Well, I don't see it being defined at y equals 0, right? Its domain, remember, was from negative infinity up to -1, including -1, and then it jumped to +1 and then on up to infinity. So it is not defined. So you can say that no solution here. Okay, and then so that part's done. Now we're going to look at sec x equal to -2. So I'm just going to extend the page here if I can. Okay, so now we're going to look at sec x equals -2. I'm just going to say that if I have sec x equals -2, then I know that the cos of x is going to equal -1/2, the reciprocal, right? So I'm going to solve for this. So x is going to equal cos inverse of -1/2. Well, -1/2 is one of our special angle ratios, so we can figure out by drawing out the triangle that has 1 and 2 in it and √3. So let's draw √3. This is then pi/3, 1, 2. If we're taking the cos of this, then it would be again pi/3. So we would say beta is equal to pi/3. This is -1/2. We know that cos is negative in quadrants 2 and quadrants 3. And so our two solutions would be x1 equals, quadrant 2 would be pi minus pi/3, which gives us x1 is equal to 2 pi/3. That's our quadrant 2 angle. And then for x2, our second angle, we have to go to quadrant 3. We're saying it's going to be pi plus pi/3 for quadrant 3. So x2 equals 4 pi/3. That's quadrant 3. So therefore, x1 equals 2 pi/3 and x2 equals 4 pi/3. Okay. All right. That's solving linear and quadratic I'm so tired. Trigonometric equations. Okay. Now we're going to get into something a little more complicated. Those are pretty straightforward. I don't know if I gave you time to copy that all out. Sorry, I'll just refer back for a second. And then now we're going to go on to something a little more complicated, but it's not too bad. You should be able to follow it. So now we're going to do double angles. So if you have a double angle, that means that you've got something's happened to your period. You've got a k value in there, right? So let's go ahead and start. There's the steps, but we'll just do it. So it says solve for this one. This one happens to be linear, so we're going to say we're going to isolate in the way that we talked about earlier. So move the 1 over, and we're going to have 5 cos 2x equal to 4. We're going to divide both sides through by 5. We're going to get cos 2x equals 4 over 5. Now this is where you have to be careful. You cannot factor that 2 out. That has to stay there intact for now. So what we're going to do is we're going to treat this like one angle for now. So you're going to take the inverse cos of 4 over 5. And again, if you could, you would come up with the angle if this was a special angle ratio, but it's not. So you're just going to say 2x is equal to cos inverse of 4 over 5. So we're going to get the angle for double for now. We're not going to solve for x. We're going to solve for 2x. Okay, so when I do that on my calculator then, because it really is a calculator angle that we're getting here, we're going to get, so shift cos of 4 divided by 5 is 0.64. So 2xc is equal to approximately 0.64. Now, cos is positive because we're looking here at the positive, in quadrants 1 and quadrant 4. Well, this is our quadrant 1 double angle here. So we could say 2x1 equals approximately 0.64. That's like our beta, remember? So we could call it beta as well if that helps. Beta is exactly or approximately 0.64. Okay, to get our second instance, we're not going to divide through yet. We're going to say 2x2 is approximately equal to, so how do we get our quadrant 4 angle? We take 2 pi and we subtract our beta 0.64. So 2x2 is equal to 6.28 minus 0.64, which is 5.64 approximately. Okay, so we didn't want the double angle, we want to solve for x, and we know that this angle here, this 2 means that there are 2 cycles of this over 2 pi. So what's happening here, if we did a little graph and we visualize this, the cos of 2x looks like this. 1, 2 cycles over 2 pi. So if I want to know where cos is equal to 4 over 5, I'm going to go to 4 over 5 and I'm going to have it here and here and here and here. There are 4 instances of this particular ratio over 0 to 2 pi because we have 2 cycles of this. Okay, so what I want to do here is once I've generated both of my first angles, I can now go ahead and divide through to get the actual x value. Okay, so x1 is going to be equal to 0.64 divided by 2. So of course that's just 0.32. x2 is equal to approximately 5.64 divided by 2, which is, let's see, 2.82. And these are all rads. I will make sure I write rad in my final answer at the very least. Okay, and now I have these 2 instances right here, the first 2. I need to get the next 2, and I'm going to use the idea of coterminal angles now. I know that there is an angle that is coterminal to x1. This one and this one are coterminal. See, they occur in the same spot for the cosine curve. So I know that all I have to do to get x3 is I have to add the period of this graph to this to get this one. So the period of my graph here, because I had a 2 cos 2x, is pi. So I'm going to say x3 is 3.14 plus 0.32. So x3 is approximately equal to 3.46 rad. And to get x4, I'm going to do exactly the same thing, except I'm going to take this one, 2.82, and add 3.14 to it. So x4 is approximately equal to 5.96 rad. And I'll summarize, therefore, x1 is approximately equal to 0.32 rad. x2 is approximately equal to 2.82 rad. x3 is approximately equal to 3.46 rad, and x4 is approximately equal to 5.96 rad. So let me just summarize here what you have to do. You're isolating again for your double angle, okay? And you're doing the same exact thing you would do now. You're figuring out on your calculator what double angle will give you this ratio. You're leaving it intact for now because you need sometimes to use that value to generate your beta or your reference angle, which I did do here. And then I'm going to come up with my second instance of this. So that's this one over here, but I'm using again I'm not using the new period, I'm using the old period, the way we were doing it before. If I wanted a quadrant 4 angle, I had to take 2 pi minus my beta, right? So I do all that, and then I find my x by dividing through by the 2. So I do that for my x1 and my x2, and then I generate the next two instances by adding the new period of this cosine function, which we know because it's 2x, we know that that period is pi because there will be two instances of it over 2 pi. So that's why I was able to generate the next two just by adding pi to the previous two. Okay? All right, we're almost there. The range of an arrow shot from a particular bow can be modeled by the equation r equals 100 sine 2 theta, where r is the range in meters and theta is the angle in radians above the horizontal that the arrow is released. A target is placed 80 meters away. What are the restrictions on angle theta? Well, okay, so it's the angle from the horizontal. Oopsie, it's not horizontal. Okay, the angle theta is the angle in radians above the horizontal that the arrow is released. Well, I'm pretty sure you do not want to be releasing an arrow straight up in the air, because if you do, there's a chance it might land on your head, right? So if you're trying to hit a target over here, you are going to be releasing it on some trajectory that is less than pi by 2. So I am going to say the restrictions on the angle are going to be that, I mean, can you have an angle of 0 from the, I think you could, so we'll just keep that one in there. So we'll say theta is an element of 0, and let's just say it would be really dumb to shoot it straight up in the air. Okay. Determine the angle or angles that the archer should use to hit the target to the nearest hundredth of a radian. Well, we know that if the target is 80 meters away, and r is the range that the bow can, not the bow, the arrow can travel, then I'm going to put 80 here. So now I want to solve for theta. I want to find the angle that the archer should aim at in order to hit the target 80 meters away. So I'm going to divide both sides through by the 100, and I'm going to get 0.8 equals sine 2 theta. And now I'm going to solve for 2 theta. So I'm just going to switch it over. 2 theta sine, oh goodness. Oh, I'm going to erase that. Okay. It's going to be sine 2 theta equals 0.8. Now I'm going to detach the 2 theta, the double angle, equals sine inverse of 0.8, and I am just going to use my calculator and find this the inverse of sine inverse of 0.8, and that's going to be, so 2 theta is approximately 0.93 radians. Okay, 0.93 radians, well, that is between 0 and pi by 2, so I'm going to consider that one to be good. Let's see if there are any more. If I get the next one, sine is also positive in quadrant 2. So if I got 2 theta, so this is, you could call this 2 theta 1. And then 2 theta 2, if I wanted to get the next instance, so I got this one is 0.93. If I want this one, then I'm just going to have to do 3.14 minus 0.93. So 2 theta 2 is going to be 3.14 minus 0.93, and that's going to give us 2.21. Now, 2.21 is greater than pi by 2, which pi by 2 is 1.57. But remember, I have to divide through by 2, so I know that I'm going to get less than 1.57 when I divide through by 2. So, theta 1 is going to be 0.93 divided by 2. So theta 1 is going to be 0.465 radians, approximately. And theta 2 is going to be 2.21 divided by 2 when I divide both sides here by 2. So theta 2 is approximately equal to 1.105 radians. And that definitely is less than pi by 2. And so these are two possible, to the nearest hundredth. So I should be rounding this up. So let's just fix that. So theta 1 is approximately 0.47 and theta 2 is approximately 1.11, and we would say then the archer should release the arrow on an angle of 0.47 radians or 1.11 radians to reach the target. Okay, so double angles, very similar to what you're doing at the beginning, except there's that one extra step where you have to find the two instances over 2 pi and then divide through by 2 and then use the period of the new function to generate 2 more. All right, good luck with everything.